that what you guys get? So our T star is 2.042. Okay, so I'm going to put all of these together. Alright, I'm going to leave these numbers over here. Okay, so our confidence interval is centered with the estimate plus or minus our t times our standard error. Okay, this is a general form for a confidence interval always. So we're going to put in y1 bar minus y2 bar plus or minus t star times s1 squared over n1 plus s2 squared over n2, and this becomes negative 4.2 plus or minus 2.042 times 1.771. So you get negative 4.2 plus or minus, and I'm just going to round off to 3.6. It's like 3.616, so 3.62. But just for simplicity, I'm going to round off to 3.6. Okay? So negative 4.2 minus 3.6 gives me negative 7.8 to negative 0.6. Okay? Alright, so what I'm going to say is, so this is our confidence interval for mu1 minus mu2, or the average runtime of soccer players and the average runtime of baseball players for 200 meters. Okay? So I would say I'm 95% confident that the average running time of soccer players is between 7.8 seconds and 0.6 seconds shorter than the average running times of baseball players. Okay. And actually, I'm just going to switch these two numbers around, just because in English we generally say the smaller number first. We have that. Okay. So I would say I'm 95% confident that the average running time of soccer players is between 0.6 and 7.8 seconds shorter than the average running time of baseball players. Okay, so we're talking about the mean in the population for soccer players versus baseball players. And so here we would say we have evidence, at least some evidence, that the average running time of soccer players is faster than that of baseball players. Does that sound okay? Okay, so if I had chosen to do baseball players minus soccer players, so I did 33.4 minus 29.2, the only thing that would change is that this would become positive, right? I would have positive 4.2. Okay? The t and the standard error, this would all remain the same. Okay? So if I change this to positive 4.2, and I have positive 4.2 plus or minus 3.6, I would end up getting 0.6 to positive 7.8. So how would that change my interpretation? Well, I would say, in this case, because I've done baseball players minus soccer players, I would say I'm 95% confident that the average runtime of baseball players is between 0.6 and 7.8 seconds longer than the average runtime of soccer players. Okay? So we're saying the exact same thing. It's just one way I can say it is soccer times runtime is shorter than that of baseball players, or I could say baseball players' runtime is longer than that of soccer players. So your choice of group 1 minus group 2 or group 2 minus group 1 doesn't really matter. You're just going to get the negative of the other situation. Okay, is that all right? Okay, so using that, make a confidence interval for the difference between the mean IQs of men and women. Okay, so using what you learned there, so I'll leave this up. This is the relevant see if you can make a 95% confidence interval. For mu1 minus mu2. Okay. Maybe just so we're all consistent, we'll call men group 1 and women group 2. And that way we'll all have the appropriate plus and minus. But again, it doesn't really matter. Okay. You guys need another minute, or are we good? Alright, did we get -9 to 12.4? No. mess something up? I might have. Huh?
Yep, plus or minus 10.4.
10.4? Let's see what I got. What did I do? I got alright, let's see. Maybe I probably messed up then. So I have
Is your N1 correct?
oh, wait a second. I don't know. Okay. Negative 1.7 plus or minus so we have 33 degrees of freedom. We round down and we choose 30 degrees of freedom, so I'm using oh, this is where I messed up. 2.042, right? 2.042 times 15.1 squared over 15 plus 14.8 squared over 20. Negative 1.7 plus or minus 2.042. Here I got 5.114. Okay, yeah, I chose the wrong T. So 5.114 times 2.042, yeah, 10.4. So negative 1.7 plus or minus 10.44. So that takes me to 12.1 and 8.7. So negative 2. So minus, wait, no, I'm messing this up. Minus 8.7 to positive 12.1, sorry. No, the opposite, just the opposite.
The
What am I doing? What am I doing?
78%, it's 50.1, and you only put 15.0
Did I?
on the standard deviation for that.
No, that's right.
Just do negative 12.1. Negative 12.1.
Negative, okay, sorry. I'm a mess. Okay, negative 12.1 to 8.7. That's correct. Okay, we're good. Alright, so what does this say? So if we were to make a sentence based on this, so my confidence interval for mu1 minus mu2 is negative 12.1 to 8.7. Okay, this is for the mean IQ of men minus mean IQ of women. So what does this tell us? Well, I would say something like, I am 95% confident that the mean IQ of men is between 12.1 points lower and 8.7 points higher than the mean IQ of women. Okay, what does that even mean? Well, this isn't really saying much, okay? All we're saying, if somebody says, is there a difference between the mean IQ of men and the mean IQ of women? My answer is basically saying, maybe the mean IQ of men is either lower or higher than the mean IQ of women. Okay? That's not a very useful statement here. Okay? So when your confidence interval includes the number 0, okay, meaning 0 is between negative 12 and positive 8.7, okay. difference between the means of the populations. Okay, so this comes back to the idea of statistical significance, right? So here, when we looked at our sample of data, we have the mean IQ of our sample for men is 98.7. The mean IQ for our sample of women was 100.4. So the observed difference is 1.7 or negative 1.7. Okay? And when we create the confidence interval for the difference in the population means, we find that that confidence interval includes the number 0. So it includes the number 0, which means we do not have evidence we do not have evidence that there's a difference between the means of the populations, meaning the means of the populations could actually be equal. So this observed difference of negative 1.7 is not statistically significant. Yes?
What is that, like the difference in absolute value though?
No, I mean it doesn't matter. Okay. So at the end of the day, we get a difference that goes from negative 12.1 to 8.7 as the confidence interval for mu1 minus mu2, as the confidence interval for the difference between the population means. Okay? So that interval contains 0, so that means our observed difference is not statistically significant. On the other hand, when we looked at the soccer players and the baseball players, the resulting confidence interval did not contain 0. It went from 0.6 to 7.8 or something like that. So that confidence interval did not contain 0. If the confidence interval for mu1 minus mu2 does not contain 0, so meaning the entire interval is entirely positive or the entire interval is all negative, then we do have evidence that there's a difference between mu1 and mu2. And then we would also say that the observed difference mu1 of y1 bar 1 minus y bar 2 is statistically significant. If the confidence interval doesn't contain 0, then we do have evidence that there's a difference between the population means. And we would also say that the observed difference is statistically significant. Yes?
For the differences, if one is negative, then you would say below,
Uh-huh.
and if it's positive, then it's higher.
So if you do the mean of group 1 minus the mean of group 2, and that ends up negative, then in your corresponding interpretation you'd say we have evidence that group 1 is lower than group 2. Okay? You could also flip it around and say group 2 is higher than group 1, but then you're switching signs around. So just make sure that your statement makes sense in terms of the numbers that you're observing. Okay. So here what we observed was the average of our sample for men was lower than the average of our sample for women. Okay. And so that's why our confidence interval is more negative than it is positive. Okay. If you have a confidence interval for mu1 minus mu2, it doesn't contain 0, we would say we have evidence that that there is a difference between mu1 and mu2. So when we looked at the baseball player and the soccer player data, we came to the conclusion that the average runtime of soccer players is shorter than the average runtime for the baseball players. Is it possible that the average runtimes are actually the same?
Yeah.
Yeah, it's possible. What would have had to have happened if that was the case?
The sample mean for baseball players would have had to been lower.
Yeah, so if the population time, the mean times in the population were actually the same, it means we had to observe, a fairly unusual sample for the baseball players in that it was too high, and a fairly unusual sample for the soccer players in that our sample was too low, leading us to believe that there is a difference when in reality there isn't. Okay? And so all of these things, again, when we make the confidence intervals, come down to we're just confident about our statements. The populations could, or population mean values may actually be inside the interval, or they may not be. And that's just, is our data unusual, or is it a routine scenario for us to end up with something like that? Okay. Statistically significant does not necessarily mean important. Okay? So, if we observe a difference, okay, so here this difference of 1.7 points, IQ points between the average here, was not statistically significant. Okay. We might have a scenario where we do have something and the difference is statistically significant. But the difference may not actually be important. Okay, so for example, let's say I don't know, we looked at some name brand product versus a generic product. Okay, so we looked at maybe we looked at name brand batteries. And generic batteries. 100 name brand batteries and 500 generic batteries. And we looked at voltage after 12 hours usage in the flashlight. Okay, so we had some kind of factory conditions. We put a bunch of batteries into a bunch of flashlights. We ran the flashlights for 12 hours and we measured the voltage at the end of the day. Okay. So our observed difference between the Y bars is 0.06 volts. Okay. All right, let's make the confidence interval. Okay. So,
105 volts.
oh, 0.05. Sorry, can't even. I'm a mess today with my nah. Okay. So let's do this. 0.05 plus or minus. Well, I guess if we're rounding down, I should have used one more in each sample, so we could just use 1,000 degrees of freedom. But we'll play it safe. We'll use 140 degrees of freedom. And so we'll have 1.977. Okay, because I have 998 degrees of freedom. We should probably use 1,000 degrees of freedom, but just so I follow the rules that I established, we'll use 140 degrees of freedom. So 1.977 times our standard error, 0.03 squared over 500, 0.04 squared over 500. And what do I have? .002? Is that right? Did I mess that up? No, that's right. 1.977. Okay, so I have 0.05 plus or minus 0.004. 0044. So my confidence interval ends up being 0.0456 to 0.0544. So the difference in voltage after 12 hours of use between the generic and the name brand batteries, is it statistically significant? Yes. Why?
Does it make
Because it doesn't contain zero. Our entire interval is positive. There's no zero, so it is statistically significant. And we would say we have evidence that the name brand batteries have a higher average voltage usage than the generic batteries. Okay? So it is statistically significant. Okay? But somebody in the industry might say any voltage difference less than 1/10 of a volt is not important. Okay, so if someone says maybe so if the voltage difference under 1/10 of a volt is not important, then even though we have evidence that the difference is statistically significant, this difference is not important. Okay. So you could have a statistically significant result, but that result may also not be important in terms of the context of whatever you're looking at. Right, so if we're looking at, I don't know, and it depends on what people and experts in the field would say is important or is not important. Okay? Important is more of a subjective thing. Okay, we don't have any mathematical rules to decide whether a difference is important or not. So somebody would have to, some expert in the field would have to say, this is an important difference or not. All we can do with statistics is to say whether this difference is significant or not. Okay? And when we say it's statistically significant, what we're essentially saying is that we would not see this kind of difference happen just from random chance alone. Okay, so from random chance alone, it is very unlikely for us to see a difference where we get 1.21 over here and 1.16 as the average over there. The confidence interval shows that. But is it important? That's a different question, and it comes down to this. Okay. Let me see if there's anything else I want to add to that. Okay. Yeah, so I guess if you ever read research papers, or if you do research yourself, you might be chasing a significant result. You might be chasing something that's statistically significant. But the question we should always be asking is what I'm chasing actually important? Okay, and somebody else needs to, some expert, you yourself or someone else might have to just judge whether something is important. You might come up with a new process, you know, a new chemical or a new something that makes a statistically significant difference in people's lives or treatments. Okay, so maybe there's a new drug that helps, you know, people's health improve. Okay, so let's say maybe the mortality rate for some disease is, I don't know, 10%. Okay, and maybe with the current treatment, the effectiveness is that 10% of people die. And maybe you come up with a new drug, and after many trials and things like that, you find statistically significant evidence that the mortality rate under the new drug is no longer 10%, but it's now 9.87%. And that difference is statistically significant. The question is that an important difference? Okay, maybe and we might say, well, we're saving people's lives, so even if it's only 0.17 of a percentage, it is important. But perhaps this new treatment is very harsh. Maybe the quality of life under this new treatment is worse compared to the classic treatment. Okay, this is something that needs to be weighed. Okay, you can't just say it's more more effective, statistically significant, it shows that it's more effective. We have this kind of reduction in the mortality rate. There's a lot of other factors that are involved. So maybe if the treatment, is really hard on the person and makes their life miserable, maybe it's not worth that extra 0.17 of a percentage to do that, okay? Of course, that's everybody's individual choice as to whether or not they should go with this or not, but statistical significance is not everything. It is important. That's what we learn in statistics, whether a difference is statistically significant or not, but it may or may not be important. So that's something else. Okay, we're going to, well, that's it for new material. Okay, I should, rather than say we're over, I should ask if there's any questions that you have in terms of stuff for the midterm exam. Yes?
So, I just had a general question.
Okay,
Is
absolutely.
95% confidence interval something that's used like in the real world?
Yeah, so we can make any percent confidence interval we want, okay? For some reason, the industry standard is 95% confidence, or this 5%, what we call it 5% alpha. And we'll learn about alpha and significance level later. For some reason, that has become the number, the de facto number of choice, but if you as a researcher decide to use a different number, you are entirely allowed to do so. Okay. In the United States, we say 18 is the year you can start voting and join the army. 21 is the year you can start drinking. If you go to Canada, they have age 19. It's different, okay? Is one country right and one country wrong? Not necessarily, okay? But that's the, these are the numbers that come to be standard. So I'll happily take any questions for midterm review. Yes?
I just have a question. We have a lab on our homework for this coming week, but it's not due till after the midterm.
Correct.
Does that mean that it's on that material is not going to be covered on the midterm, or?
The material in the lab is not covered in the midterm. Actually, let me do some stuff from that lab. Sorry, you guys. I should do that because I know you guys will run into problems and well, I'm not saying everyone will run into problems, but I have a feeling that some of you will run into problems and some parts of the lab will be frustrating. Okay, but I guess before I do that, other questions? Yes?
Are we ever going to need to apply a one-tailed t-test versus a two-tailed?
Yes, but after the midterm. So that's chapter 7, okay? So the midterm you are responsible up to everything we covered in chapter 6. Anything else? Okay, so I'm going to hop on here. Thank you for reminding me about the lab. I don't want to leave you hanging.
It's like 9:30 again? Or 5:30? I was going to do one right here, but that's a little more classy than that. What is this? Dude. How you hanging with class? Huh? Me too.
Okay, so this lab,
Me too.
use these PDFs. So in lab assignment 2, again, this is going to be due the week after the midterm. Okay, so the midterm is next week. You just have to complete just a few exercises from chapter 6. Okay, and then this is the about the midterm page, or it just talks about stuff you need to know.
This this homework, that's homework 5.
Yes.
It's question from chapter 6. Is that stuff going to be on the midterm?
Yes. Okay, so that's the stuff I covered today. That stuff's going to be on the midterm. Okay. Lab assignment 2. I'm assigning it now, but it's not due until the week after the midterm. Okay. So you're going to start doing like making confidence intervals and stuff. Okay, so anyway, you click the thing, and you get, it takes you to this PDF, okay? And we're looking at real estate data from Iowa. And they just look at a whole bunch of stuff, all right? And so, oh gosh, I did not want to like that. Oh. So some of these things are, was there a question? Okay, so a lot of these code snippets creating I have a blank source file that I've made with an R script right here, and so I can enter my text here. All right, so I'm just going to run this and just make sure this runs. Okay, good. So now I have, so the data has loaded. You can see it right here. And we have, there's 2,390 observations, 82 variables. There's a whole bunch of them. Okay, a lot are categorical, and some are numeric. We want to we can do some stuff here. Okay, so we're going to take this this column gr.live.area, okay, which is the ground living area in the house, and we're just going to create a vector called area. All right, so all of these codes, I recommend typing. Well, I recommend reading the text and then typing the commands as you see them. Okay, so rather than copy and pasting, I feel it's better to type them out. Okay, the $ indicates use the column within the data set names. So all we're taking is the values from living area, and then we've got price. Let's take a look at the area. So we can do summary area, and it gives us some stuff, and then we can ask for a histogram of area. Okay. Speaker margin's too large. That's just. Okay. So what we see is we see something that's right skewed. And most houses are between 1,000 and 2,000 square feet, but we do have some very large houses. Okay, so we do see, yeah, there are some, not very many houses over 3,000 square feet, nearly most of the houses are between 1,000 and 2,000, maybe some of them 900. Very few houses that are much smaller than that. Okay, so we have, we're going to use this function sample, okay, which I used last week. And all sample does is it goes to the listing area. So just, I'm trying to do this. So if we take a look at area, it's 2,930 numbers, okay? It says ints or integers. We've got 2,930 integers. Each one corresponds to the square footage of the house, okay? So the very first one is a house with 16